Yeah, so then why does that mean the original series converges? The one without the absolute value of the ANs? Why? Drew? So if the sum of the ANs converge, why so why does this give us what we need?
Well, when we proved that comparison test,
Mm-hmm.
we did it with the absolute value of the AN, of the smaller one.
Uh-huh.
Implied that the bigger one, then the non-absolute value converged.
Yeah, so we actually have what we need, right? Yeah, that's right. Yeah, so actually we don't need to say this, right? Yeah, so the comparison test actually gives us this. We just need this thing to be smaller. Okay, excellent. So what about if alpha is bigger than 1? What do you think happens? What goes wrong when alpha is bigger than 1? Well, that means this lim sup is bigger than 1. That means what? Eventually what? Or not eventually, but the fact that lim sup is bigger than 1 means that there's a subsequence that converges to something bigger than 1. But if the subsequence converges to something bigger than 1, basically that means the terms don't go to 0, right? That's the intuition. So there exists a subsequence, sum of, let's say, n sub k, a sub n k, that converges to some alpha bigger than 1. So what? Well, that means a sub nk is bigger than 1. I mean, this converges something bigger than 1, then this thing is going to be bigger than 1 for infinitely many terms. So the terms don't go to 0. Terms do not go to 0, so the series diverges. There, that's the basic message. Okay. And so then the final case is, what if alpha is 1? Well, the test is inconclusive. You might say, well, haven't we already, is there anything to show? Well, yeah, there is something to show. I want to show you that there are examples of series that, for which the ratio test gives the ratio 1, and the series diverges, and other examples where it converges. So if alpha is 1, you can check that. Notice that the sum of 1 over n diverges. The sum of 1 over n squared converges. And for both of these, they both have alpha equal 1. Okay? But what's the basic message? Compare with the geometric series. All right. Here's another test, a famous test, the ratio test. It's the cousin of the root test. Now, the ratio test says to look at what? Anybody remember? You want to check a series converges? Look at the ratio of successive terms. Okay, good. Let's just say what the test is. So the claim is the sum of the ANs converge if what? Well, what do I do with those ratios of successive terms? I take their, yeah, okay. You might say take their limit, but again, the limit may not exist. That's a high school version, right? You give a simple case. But in this case, we're going to look at the lim sup of the ratios an plus 1 over an, a sub n plus 1 over a sub n. And I'll look at this lim sup, and it converges if this lim sup is less than 1. Very good. And it diverges if what? Well, yeah, I'm going to say it this way. The sum of a sub, the ratio of a sub n plus 1 over a sub n is bigger than or equal to 1 for n large enough. Okay, for all n bigger than some number. Okay. Now, it has a similar feeling as the root test. The thing I just want to leave you with is the root test is actually way more powerful. But the ratio test often is easier to use. Okay, so this is easier. The root test is powerful. The ratio test is easier. Often easier to use, if you can use it. Okay. Okay. Now, so, I mean, the ratio test, I mean, the reason that it's not always so powerful is that there are sequences which converge, but for which this ratio thing is, it doesn't give much information, right? So you might imagine a sequence like, how about this one? 1, 1, 1 half, 1 half, 1/3, 1/3, ... Well, this ratio of successive terms, every other ratio is going to be 1 here, isn't it? Right? 1. Here, let's make this more easier. 1/2 to the 1/2, 1/4, 1/8. So basically, the successive ratios here are 1, 2, 1, 2, 1, 2, etc. Yeah? And so, did I have that? I guess it's 1/2. Okay, and so what do I have here for this sequence? Well, this test, the ratio test here is not going to tell me very much, right? And it's just because you have this kind of funny situation. Oh, that looks like a smiley face. Oh, they all do. That's cool. I didn't even intend that. So that's why the ratio test is maybe not always so powerful, but it's certainly helpful in many cases. Okay, so how are we going to prove it? Comparison again. And I'll just sketch this for you. Would you agree that because the lim sup is less than 1, once again, there's a beta in between for which this is eventually less than beta? That's the same idea. So then basically in the first situation, we have a sub n plus 1 over a sub n is less than beta, which is less than 1, for some beta, and for n bigger than some n. This is a sketch. I'm just giving you the highlights. It's like that argument. Now what? Why is this going to help me compare? And what am I going to compare to again? Geometric series. Tell me, give me the intuition. Why is this going to help me compare this to the geometric series? A sub 1, n plus 1 is, Richard's thinking, oh, look, it's like less than a beta a sub n, right? So each time I'm introducing at most a factor beta. So we have a sub n plus 1 in absolute value is less than beta a sub n. Yeah? But wait, what's that? I could keep going here if I wanted. Beta squared a sub n minus 1 less than beta cubed a sub n minus 2, etc. But what you find eventually is